Hey board physicists.
Point 3. Probability. Due to the statistical interpretation, understanding probability is a must for understanding quantum mechanics. So we will discuss the theory of probability in this section. To understand notations and terminologies, we can approach it with an example. We also recommend you check out the videos with exercises featured in the playlist, especially questions 1.1 to 1.6. Now, the example. We can consider 14 people with different ages as shown in this table below. The probability of a certain outcome J is given by the following equations. So P is the outcome of J, N of J is the frequency of the outcome, and N is the total frequency, which can be expressed as this sum. So for this case, for example, the probability of guessing age 16 is 3 out of 14, and the probability of guessing either 14 or 15 is the sum of individual probabilities, so 1 out of 7. The total probability is always 1 because you're certain to get some age. So this can be expressed like this. The most probable outcome is the outcome that occurs the most. So here it would be age 25. The median outcome lies exactly in the middle of the outcomes when the outcomes are written in ascending order, or the outcome such that the probability of getting a larger result is the same as the probability of getting a smaller result. So in this case it would be age 23. The average or the mean is expressed like this and given by the following equation. In this example we can calculate this to be 21. The mean and the median age do not have to be part of the original sample of data. So notice how nobody is actually 21 or 23. In quantum mechanics, the average is the quantity we are most interested in, and for some reason it has come to be known as the expectation value. It's a bit misleading, but we just have to remember it means the average. We can also calculate the average of the squares of the terms, which can be done by the following equation. So in general, the average value of some function f of j is given by this equation. Beware, the average of the squares is not ordinarily equal to the square of the average. Now take a look at this. Although the median, the average, and the most probable values are equal for the two histograms, the standard deviation is not. What is the standard deviation, you may ask? The standard deviation is a numerical measure of the amount of spread in a distribution with respect to the average. So to calculate this, we find out how far each individual value deviates from the average value and then calculate the average of the value. But when we calculate the average, we get 0. Using the general definition of the average here and here, we have taken out the average of j from the summation because it's a constant. Then we can calculate the average to be this, but it's 0. To avoid this 0, we might instead try to average the absolute value of delta j, but the absolute values are too difficult to work with. Instead, we can square the values to get the standard deviation squared, which is the variance given in the sigma squared. Whereas sigma itself, the square root of the average of the square of the deviation from the average. This is the spread about the average of j. Using some algebraic manipulation that you can find in the book, we can also obtain this expression for sigma squared. Since sigma squared is non-negative, the following must be true and can only be equal to 0 when we have the same value, i.e. the spread of the distribution is 0. So far we have assumed that the distribution consists of discrete values only. If we consider continuous variables, we can say that the probability of obtaining a value between x and x plus dx is rho dx. The rho is the probability density, and the probability x lies between a and b and is given by the integral of rho dx, the finite integral, which is represented by this. The following rules of discrete distribution can be seen here, and the rules for the continuous distribution can be seen here. The rules for the discrete distribution can directly translate into the continuous distribution.
1.4 Normalization.
From equation 1.16, there is a condition that the integral of the modulus squared of the wave function must be equal to 1, because the particle must be somewhere between minus infinity and plus infinity. The wave function phi is supposed to be determined by the Schrodinger equation, and if we look at the Schrodinger equation, we see a phi is also a solution where a is any complex number. But we have to choose this factor a to ensure that this equation is satisfied. The whole process is called normalizing the wave function. Some solutions to the Schrodinger equation where this equation is not satisfied, so they're known as the non-normalizable solutions. E.g., if the wave function is 0 or infinite, these can't represent particles. So if such solutions are found, they're rejected. But as time goes on and the wave function evolves, will the wave function stay normalized? We have to realize we can't keep on renormalizing the wave function a phi. Otherwise, a becomes a function of t, which is no good, because then a phi is no longer a solution to the Schrodinger equation. The solution to that is that the Schrodinger equation has the property that it automatically preserves the normalization of the wave function. This is a very important feature of the Schrodinger equation and is one that makes it compatible with the statistical interpretation. If we take out the partial derivative of x, we can equate the expression to an integral that is a function of t. So we can then use the total derivative d dt
One.
Hence the integral.
Bored physicists.